So we're now ready to prove condition 3 implies condition 4, basically the existence of these sequence of finite support positive definite function converging point 1 to 1 will imply the full and reduced C-star algebra are the same. All right, so let us clean up what we did from last time. We proved a little technical lemma, so let me just try to draw this commutative diagram. That's kind of a standard way of proving things when you try to prove mutability, or in terms of the full and reduced. The thing is, you have the C-star algebra of G, and we define this map M of phi alpha. Basically, they just multiply on these group algebra, and then we saw you can extend it to a positive map to the full C-star algebra, and they have normal 1. So, and on the other side, you can use your left regular representation that maps from your full C-star algebra to the reduced one. So here I have 2 copies of the reduced. And you also have another map. This is M bar of phi alpha. We didn't prove it, but it's really just following very similar argument. I can show you also have a norm 1 positive map defining using these phi alpha. So the key idea is that, well, to show that this lambda is going to be injective, that's why this suffices for lambda being the isometric isomorphism. So to show it's going to be injective, you actually know that this lambda is injective on the group algebra. So this is observed. This is usually that's how you use these kind of commutative diagram, is that so lambda is injective on your group algebra, so on C of G. The reason is very simple, because well, if you take any finite linear combination of in the C of G, and you take a lambda, for example, you take a lambda times summation of some alpha t dot t. Okay, so it just maps to the summation of the alpha t times the lambda t. Okay, so lambda t is your left regular representation, and this is a very concrete operator. So this is in the bounded linear operator on the L2 of G, and you can just think about, well, sum of the alpha t has to be non-zero. And if you look at what happens when you try to translate one vector, say the delta E, the one of the basic vectors, the lambda t will map it to the delta t. Okay, it's a left regular representation, so this shifts your orthonormal basis by t. And so one of these alpha t is non-zero, so it will map some non-zero orthonormal basis to a non-zero vector, so it's certainly non-zero. Well, if it's 0, of course, all of the alpha t have to be 0. Okay, so basically lambda of this summation is equal to 0. That's even only if alpha t is equal to 0 for all t. So let's just prove that lambda is indeed injective on this C of G. The only problem when you actually complete to the uniform, the universal C-star algebra, well, some of them may not be injected anymore, but when we have these kind of intertwining map, then this cannot happen as well. Okay, so let's see. So because the way I defined these M map, this diagram is really commute. So what I mean is that if you compose lambda with your M of phi alpha, that's going to be equals to you compose the other way, but using the M alpha on the reduced, so M bar of the alpha composed with lambda. All right, so because your phi I is converging to 1 in pointwise sense, okay, so that just implies if you look at M of phi I of some x, okay, for every x inside your group algebra, okay, your x is finitely supported, so because it's finite supported and these phi I are converging pointwise, so you only care about these finitely many entries, that will convert to x, okay? But because your M phi I can be extended, I should say phi alpha probably, but because it's extended to a norm 1, at least at most norm 1, so basically this property will preserve when you close it up in the uniform C-star algebra, so the universal C-star algebra. So basically for every x inside the C-star of G, you also have these M phi alpha of x converging x in the universal one, all right? All right, so now let's suppose I have something that's in the kernel of my lambda. So let's say lambda x inside the full C-star algebra. And so if I have a lambda x equals to 0, then you use this commuting relation. You let's plug into the right-hand side. So your lambda composed with n phi alpha of x. Okay, that's going to be equals to n phi alpha bar composed with lambda of x, but lambda is equal to 0. This means this is also equal to 0. So this basically just translates to each of these n phi alpha of x being 0. But now you see that the n of phi alpha basically, so n of phi alpha of x, because your phi alpha, the support of this phi alpha is finite. Okay, so imagine your x may be some infinite combinations, but the phi alpha will kill off, basically only preserve finitely many of these. So essentially, this is going to be finitely supported. So this one is actually inside the group algebra. Okay, so this is in the C of G, and because it's in the C of G, and we have the lambda is injective on the group algebra. So lambda injective on the C of G. Okay, so automatically I have that whatever I have here. So m of phi alpha of x that has to be equal to 0. Okay, but we just saw that being equal to 0, this net of n phi alpha is converging to x, so that just implies x has to be 0 as well. Okay, so this is how you use these kind of intertwiners to prove the injectivity. You use lambda is injective on some subspace. Okay, that's a fairly standard trick actually. Next week we're moving into some semigroup C-star algebra, and this is also a standard trick in there as well. All right, so now let's just quickly clean up the next one. So the 4 implies 5. These two, the full and reduced, are the same, implies that you have a character on the reduced one. Okay, that's quite easy now. So if you just consider the pi e to be the trivial representation, so in other words, the pi e of x is equal to 1. Okay, so that is a unitary representation. Okay, that's basically you treated the C as basically the bounded linear operator on C itself. Okay, so it's indeed a unitary representation, not a very interesting one. But the nice thing about it is that, well, because it's a unitary representation, it can be extended to a star representation of your L1 space. So what it does is very simple. So if you have a alpha t dot t, what it does is basically map all the t to 1, okay, the unitary 1. So you just sum up all your coefficients, okay, so that's what it does. And certainly it extends to some C-star, to a map to from the C-star algebra, the full C-star algebra to the complex. So this one you can extend it because your full really contains all of these representations. So you have a star representation, let's say pi e, going from the full C-star algebra to C. So what it does is extending your pi e on the group algebra to the entire full C-star algebra. And this one, because pi e is coming from a unitary representation, this map is really multiplicative. Okay, so this is multiplicative. It's a star representation. Okay, so pi e is now a character on the full C-star algebra. So i.e. A character on the full C-star algebra. But the full C-star algebra by 4 is isomorphic to the reduced one. Okay, so this also drops down to a character on the reduced. Okay, so now we also have a character on the reduced C-star algebra.